Here are three properties of logarithms. The logarithm of 1 to the base b is equal to 0, the logarithm of b to the base b is equal to 1, and the logarithm of b to an exponent n, all to the base b, is equal to that exponent n. I think it's much easier to see what's going on here if we rewrite these in exponential form. This first one, the logarithm of 1 to the base b, really means if b is raised to the power of 0, we get 1. If b is raised to the power of 0, we get 1. Or, reading the logarithm as a question, the logarithm of 1 to the base b is what? Or what exponent does b need to be raised to in order to have an output of 1? Well, b needs to be raised to the power of 0 in order to have an output of 1. Remember that any base raised to the power of 0 is equal to 1. An example of this would be evaluate the logarithm of 1 to the base 3. This is asking 3 raised to what power results in the number 1? Well, the output, the answer, is 0. 3 raised to the power of 0 gives 1. What about the second one? The logarithm of b to the base b is equal to 1. Well, this says b raised to what power gives b? Well, b raised to the power of 1 gives b. b raised to the power of 1 gives b. So for example, what is the logarithm of 5 to the base 5? Is asking, what does the base 5 need to be raised to? What power does it need to be raised to in order to result in an output of 5? It needs to be raised to the power of 1. And then by extension, what power does the base need to be raised to become b to the power of n? It needs to be raised to the power of n to become b to the power of n. This simply says b to the power of n is equal to b to the power of n. We might see it this way. What is the logarithm of 8 to the base 2? Well, that's not quite the same thing yet, but I know that 8 can be rewritten as 2 to the power of 3. So this might say, what is the logarithm of 2 to the power of 3 to the base 2? And now you can say, what power is 2 raised to become 2 to the power of 3? 2 is raised to the power of 3 to become 2 to the power of 3. So these are the first properties of logarithms that we'll tackle. Let's look at a few questions. We just took a crack at this very first one. What is the logarithm of 8 to the base 2? In other words, what power does 2 need to be raised to turn into an 8? We can rewrite the 8 using the base 2. 2 to the power of 3 is equal to 8. I chose to rewrite the 8 using a base of 2 because the base of our logarithm is also 2. So rather than taking the logarithm of 8, we'll take the logarithm of 2 to the power of 3. The logarithm of 2 to the power of 3 to the base 2 is just equal to 3. What about this next one? Can you rewrite 1 over 81 as 3 to some power? So 3 to what power would turn that 3 into a 1 over 81? Well, to turn a 3 into an 81, I need to raise it to the power of 4. 3 to the power of 4 is 81. And then I need to take its reciprocal to turn it into 1 over 81. 3 to the power of negative 4 gives me 1 over 81. So I could rewrite this as the logarithm of 3 to the power of negative 4 to the base 3, and then using properties of exponents, and then using properties of logarithms, I see that the answer must again be the exponent, or negative 4. This third one is already set up for us. What is the logarithm of 5 to the power of 0.1, all to the base 5? Well, as we saw before, if we have the thing we're taking the logarithm of, or at least the base of it, is the same as the base of our logarithm, the output is just the exponent. If the thing we're taking the logarithm of matches the base of the logarithm, the output is just the exponent. We see the trend one more time. We're taking the logarithm of 5 raised to a power to the logarithm of base 5. So the answer, absolutely, the answer is just the exponent, or 0.1. This last one, again, takes a little bit of manipulation. We're taking the logarithm of the cubed root of 25 to the base 5. Can we rewrite the cubed root of 25 as 5 to some power? Recall that if we're taking a cubed root, that's really 25 to the power of 1/3. And I know that 5 squared is equal to 25, so I can write this as 5 to the power of 2 for 25, 2 divided by 3 for the cubed root. So I'm taking the logarithm of 5 to the power of 2/3 to the base 5, and once again, the thing I'm taking the logarithm of and the base of the logarithm match, so the answer to this question is 2/3. The logarithm of 5 to the power of 2/3 to the base 5 is just 2/3. So we can play around with properties of exponents and this new set of properties of logarithms, which are simply tied to properties of exponents, in order to solve some logarithmic questions without using our calculators. Here's another important set of properties of logarithms. Here are the properties that have to do with the sum, the difference, or the multiple of logs. This first property addresses the logarithm of a product, in this case x multiplied by y. We can rewrite this as the sum of two logarithms, the logarithm of x plus the logarithm of y. So the logarithm of the first part of our product plus the logarithm of the second part of our product. This next one, we have the logarithm of a quotient. We can express the logarithm of a quotient, x divided by y, as a difference of logs. We'll subtract the logarithm of y from the logarithm of x. And finally, if x is raised to a power, we can rewrite this as a multiple. Once again, these are easier to see in practice. Here we're asked to express the following as a sum, difference, or multiple of logs. So we have the logarithm of 2/11 to the base 3. Well, if we have a quotient, we're looking at the second property. A quotient will turn into a difference of logs. So we rewrite this as the logarithm of 2 to the base 3 minus the logarithm of 11 to the base 3. We always subtract the logarithm of the denominator from the logarithm of the numerator. In the second question, we have two things going on. We have both a product, x times y, but x is also raised to a power. Note that only x is raised to the power of 5, not the y. So I don't want to pick up this 5 and invoke rule number 3 right away, which would tell me to pick up the exponent and write it out front as a multiple of logs, because that exponent only applies to the x. So instead, I'm going to start with the fact that we have a product. So I'll write this as the logarithm of x to the power of 5 to the base 8 plus the logarithm of y to the base 8. Next, I'll apply the property for powers and pick up that 5 and move it out front. So we get 5 times the logarithm of x to the base 8 plus the logarithm of y to the base 8. Notice that if we were moving in the other direction, in other words, starting with a sum of logs and writing them as a product, we would first have to use the multiple of logs and write that as an exponent. Because once again, the 5 only applies to the x, not to the y. This one has a little bit more going on. So we've got both a quotient, a product, and some powers. Let's tackle these one at a time, starting with the quotient. So we'll have the logarithm of z squared to the base 2 minus the logarithm of everything in the denominator. So the logarithm of x cubed y all to the base 2. So notice that we're subtracting the logarithm of everything that was previously in the denominator. So we'll tackle this second term first because now we have a product. Write this as the logarithm of z squared to the base 2 minus everything that follows in this term, and that's the logarithm of x cubed to the base 2 plus, because we have a product of x and y, so we'll add our logs, have a sum of logs, plus the logarithm of y to the base 2. The brackets here are important because both the x cubed and the y came from the denominator in our original expression. The only way for them to end up in the denominator, again if we were to go backwards, is for both of them to be subtracted. Let's deal with those powers, and we're almost done. We'll move the 2 out front to write it as a multiple, and we'll do the same thing with the 3. I'll also use distributive property here to multiply the -1 out front of the brackets by both terms inside of the brackets. So this gives us 2 times the logarithm of z to the base 2 minus 3 times the logarithm of x to the base 2 minus the logarithm of y also to the base 2. And notice that I lost a base 2 up here. One thing you may have noticed is that if I have logarithm base 2 in the question, I have to be sure that I have logarithm to the base 2 in every term of my answer. And the converse is also true. I can only add or subtract logarithms if they have the same base. If these logarithms have different bases, I'd either first need to change the base or I wouldn't be able to add them. What about moving in the other direction? So here we have a sum of logs. We're adding 2 logs together. The thing we're taking the logarithm of, be that x and y, will be multiplied together when we write this as a single log. In this case, x times y. So in our problem, these are both logarithm to the base 2, so I can write it as a single log. The logarithm to the base 2 of the product of the values I'm taking the logarithm of separately. So 3 times x. So as a single log, this is the logarithm of 3x to the base 2. For the second question, we have 2 approaches that we can take. You can consider this negative log of x to the base 8 as being a multiple. The first thing that we'll do is we'll turn that multiple back into a power. So we'll write this as the logarithm of x to the power of -1, and that's to the base 8. And then we'll add the logarithm of y also to the base 8. Since we have the same base, we can write this as the logarithm of a single quantity. So the logarithm to the base 8 of the product of x to the power of -1 and y. X to the power of -1 times y. Nobody likes negative exponents, so we're going to rewrite x to the power of -1 without using a negative exponent. So this gives us the logarithm to the base 8 of y over x, because x to the power of -1 moves the x to the denominator. An alternate approach to this problem be to recognize that I can simply rewrite the original as the logarithm of y to the base 8 minus the logarithm of x to the base 8. I can simply take the 2 terms in the original problem and reorder them. Now instead of having a sum of logs, I'm looking at a difference of logs. So this tells me I'll end up with a quotient once I write them as the logarithm of a single quantity. So we have the logarithm to the base 8 of the y over x. I know that the y ends up in the numerator because the y is a positive log, and the x ends up in the denominator because we're subtracting this log. If you recognize that from the original problem, you can jump right to this final answer. Let's look at 2 more. We'll have a little bit more work to do here. Again, in the first case, while we have a sum of logs, the first thing I need to take care of are the multiples. So I'll take 2 and turn that into a power, and likewise take the 1/2 and turn it into a power of 9. So now we have the logarithm of 3 squared to the base 4 plus the logarithm of 9 to the power of 1/2 to the base 4. And we can evaluate those. 3 to the power of 2 has a value of 9, so this is the logarithm of 9 to the base 4. And 9 to the power of 1/2 is the square root of 9, and the square root of 9 is 3, so we'll add the logarithm of 3 to the base 4. We want to simplify our final answer anyway, so if we can simplify in the intermediate steps, we may as well. Now I have a sum of logs, so I'll take the 9 and the 3 and multiply them together when I write them as the logarithm of a single property. So we have the logarithm of 9 times 3, or the logarithm of 27 to the base 4. Because these were all numeric values, it was easy to evaluate and simplify. For the last question, I'll be able to do some simplification as well, although with these x's and y's, we won't end up with a numeric answer. So first thing is I'll look for those multiples, and I'll write them as powers. So this gives the logarithm of x squared to the base 2 plus the logarithm of x, y both raised to the power of 4. Of course, the logarithm is to the base 2 minus the logarithm of y to the base 2. If I wanted to, I could also take this negative and treat that as a -1 and turn it into a power, but we do have a rule for subtracting logs, so we may as well use it. Careful here, because both the x and the y are the thing I'm taking the logarithm of. When I pull the 4 out from being multiplied by the logarithm and turning it into a power, I have to be careful that it applies to both the x and the y. Recall that xy to the power of 4 is equal to x to the power of 4 times y to the power of 4. Now I know that when I add logs, the things I'm adding end up in the numerator. They become products. And when I subtract a log, it ends up in the denominator. So I can finish this off in one step. This will be the logarithm to the base 2 of x squared times x to the power of 4 times y to the power of 4, all divided by y. Now I do have some simplification I can do inside those brackets. So to finish off this problem, I'll simplify x squared times x to the power of 4. That gives us x to the power of 6, and y to the power of 4 divided by y is y to the power of 3.